Now that we all have the files opened and our working directory set up in the correct place, let's start running through a number of software exercises and examples to illustrate some of the points that we've made with regard to rare variant analysis and testing. So what we're going to do is we're first going to play around and examine the behavior of some of the collapsing methods. That's to say, the burden-based tests where we're creating collapsed indicator variables or dosage variables for summarizing the rare variant information, which we'll then associate with phenotypes and outcomes of interest. For most of this, I'll just be running through code, and I'll tell you the line number that we're running, and then I'll also talk a little bit about what I'm hoping to illustrate with each of these points. So let's begin. The first thing that I'm going to do is I'm going to read in the variants inside of the file gene1.txt. All right, so that code is on line 5. If we simply highlight that and hit run, all right, then you'll see down here that the data are now read in. So read.table reads in the data, and as.matrix is just forcing it to become a data matrix. If we look at the dimensionality of Z, all right, it shows that there's 1,000 rows and 50 columns, which is to say there are 1,000 individuals and 50 variants measured on each of 1,000 individuals. That's to say that, again, that there's 50 variants inside of this particular region of interest. The next step is we're going to calculate the minor allele frequency. And so there's two different ways to do this. Both lines 7 and 9 are doing the exact same thing. Essentially, what we're going to do is we're going to calculate the mean of each column and divide by 2. We divide by 2, again, because these are coded additively, and everybody has 2 chromosomes. So if we just highlight that and run, all right, and then we come down to the bottom screen, we type in MAF, then we can see the minor allele frequencies. And so this is the minor allele frequency for variant 1, variant 2, variant 3, variant 4, and so on and so forth. You'll see that for the most part, most of the variants have relatively low allele frequency. So this one is 0.15%, 0.05%, but there are also a few common variants that are in there. So this one is at 14.4%, 24.3%, and so on and so forth. Line 9 is basically doing exactly the same thing. So if you run that and look at MAF, you see that you get the exact same results. And so that's just to say there's a number of different ways for estimating the minor allele frequency. What we're going to do next is we're going to plot a histogram of the allele frequencies. To do that, you just type in hist MAF. So that's line 11. So if you highlight that and hit run, then this is a histogram of the allele frequencies. The x-axis is the MAF, minor allele frequency, and y-axis, it's called frequency, but here we're just talking about the number of times something within that particular range appears. So it's just a histogram. And what you can see from this histogram is that the vast majority of variants tend to have low allele frequency over. All right, so everything is between 0 and 10% over here. But you do also have a few common variants over here, though they represent a relatively small proportion of the total variants that are within this region. One other thing that is worth noting is that you have one variant over here, which has allele frequency that is greater than 50%. And so this type of plot is very useful because it indicates that this may be something that is miscoded. In general, whenever we do our coding, we could typically code our data as the number of minor alleles, where the minor allele is simply the less common allele. And so in this case, it's going a little bit against convention, and we've coded it incorrectly. The actual reason for this is that this is a subsetted data set, and in this particular set of individuals, this one just happens to be greater than 50%. So that actually doesn't matter too much for this software demo, so we're going to ignore that for now. So that was the overall minor allele frequencies. What we're going to do in the next line, line 12, is we're going to zoom in on the allele frequencies that are the variants that have allele frequency less than 5%. So it's the same thing as line 11, except now we're just focusing on the variants that have allele frequency less than 5%. So if we highlight line 12 and hit run, then here you can see similar plot as before, except now we've zoomed in on the lower end. And so what you can see again is now, so the x-axis goes from 0 to say 3.5%. And it's the same plot as we saw earlier. Basically, everything is sitting down at the very, very low end. In fact, these guys represent singletons. That's to say variants that appear in only a single individual. And the vast majority of variants that we're looking at are singletons in this data set. There are a few others that are pretty rare, and then a few other variants which are rare, but not super, super rare. So sort of within that Goldilocks range. These histograms illustrate just a couple points. First of all, in the previous histogram, you were able to see that there's variants that may be coded incorrectly. You have to be a little bit careful depending on the software that you're getting your variant calls from. They sometimes code things a little bit differently. And the other thing here is in this data set, the vast majority of variants are indeed rare. And even among the rare variants, the vast majority of them are singletons. That's to say, appear only in a single individual. So let's close that. The next thing that we're going to do is we're going to actually do a little bit of association testing using some of the burden-based and collapsing tests. So let's go down to line 19. And what we're going to do now is we're going to read in the data for read in a trait value. So we've already read in the variance that's inside of the matrix Z. What we're going to do now is we're going to read in some outcome or phenotype information. After that, we're going to test for the association between each variant one by one and the trait value. So zy.c is going to be the variable name for our continuous phenotype, and we're just going to scan it in from the file trait1.txt. So we run that, and you should see down here something that says read 1,000 items. So there's 1,000 individuals, and we've read in one trait for each individual. If you look at what y.c looks like, it's just a whole bunch of continuous numbers. If we plot a histogram of y.c, so we type in hist y.c, hit enter, it's a very, very nicely distributed, normally distributed trait in this case, after some normalization was done. In this case, it's been centered, but there's no requirement for any centering for any of the methods that we're going to talk about today. So that's y.c. What we're going to do now is we're going to, again, as I've said, test for the association between each variant in gene 1 and trait 1, the outcome. So we initialize an empty vector of p-values for storing the p-values, and then we actually run the association test inside of a for loop down here. So just to look at the code over here, lm y.c twiddle z, comma j means that we're going to look at the association between the jth variant and the outcome by running a linear model. Typing in summary pulls out the coefficient table, and coefficient 2.4, that ends up being the p-value in this case for the association between the jth variant and the outcome here. And then down here, we're going to do a Bonferroni correction to adjust the p-values for multiple testing. So if we highlight lines 21 through 25 and we run this guy, hit run, then what we've done is now these are the Bonferroni adjusted p-values for associating variant 1, variant 2, variant 3, variant 4, variant 5, and so on and so forth with the quantitative trait 1. And so what you can see is that there are a few p-values, adjusted p-values that are less than 1, but overall there's not very much going on over here. Nothing here would be called significant, statistically significant by most standards. If you want to look at the raw p-values, we type in PVS, which is where we've stored this, and then you can see again that the vast majority of p-values here are not very small. There's a couple that look a little bit smaller, but as we saw from up here, nothing survives the correction for multiple testing. So doing marginal analysis does not call any individual variants as significant, which is what we've talked about earlier. In general, since most of these variants tend to be very rare, the power to call them as associated with the outcome is very, very low. And you see a lot of p-values that are in the higher range, so 0.97, 0.93, and so on. Next, what we're going to do is we're actually going to run some of the collapsing tests as a comparison. So we're going to first call the variants that have minor allele frequency less than 3% as rare. And so RVS equals which of MAF less than 0.03. This is just finding the indices of the variants that have allele frequency less than 3%. If we hit run, and then we look at what RVS is, then this means that, in this case, variant 1, 2, but not 3 and 4 5, 6, 7, 8, 9, but not 10 and 11, all have allele frequency less than 3% and would be considered rare in this particular analysis. So after we figure that out, we're going to first run cast, which is the binary collapsing. Recall cast creates a binary variable for each individual, 0 or 1, where if you have no rare variance, you're scored as a 0, and if you have any rare variance within this region, you're scored as a 1. So, and that's what this code over here is doing. So line 35, that's all it's doing. It's figuring out whether you have any rare variance within this region. And so if we highlight line 35 and hit run, and then let's come down here, let's type in C just to see what it is. And you see it's just a giant list of zeros and ones. And so this is individual 1, 2, 3, 4, 5, 6. And so the first 5 people are all scored as zeros because they have no rare variance within this region. Person 6 in our study is scored as a 1 because they have 1 or more rare variance within this region. The next step then is to actually do the association test. And so again, we're going to use a linear model, LM, to regress the outcome y.c on now the collapsed variable c, and just type in summary. So we highlight that, hit run. What you see over here is, so this is the call. These are the residuals, which gives you some ideas of model fit. And coefficients over here is what we're most interested in. So this is so the first column tells you the variable name. So this is the intercept in the model. And then this is the variable c, our collapsed variable. And then for each of these, we have the regression coefficient, which is the estimate. We have a standard error on this estimate, a corresponding t-value, a t-statistic, and then the PR, parentheses, greater than absolute value of t. This is actually the p-value corresponding to the p-value for each of these variables for their association with the outcome. And so in this case, we get a p-value of 0.0325. There's a little star next to it indicating that it is less than 0.05. And so what this means is that at the nominal 0.05 level, this region would be called associated with the outcome using the cast method. So previously when we did individual variant testing, nothing came up as significant. In this case, if we use the cast or collapsing approach, we are able to call statistical significance, at least at the 0.05 level. So we're going to repeat this using count-based collapsing. So, or also called Morse and Zaghini test, Granville, adaptive number of rare variants, and so on. But basically, what we're going to do is just, instead of saying each person is scored as 0, 1, based on whether or not you have any rare variants, we're going to score you as a dosage, based on the number of rare variants that each person that you may have. And so that's what line 42 is doing. So if we just highlight line 42 and hit run, and then we look at what is inside of C, you see that it's, again, just a whole bunch of different numbers, a whole bunch of zeros. All right, so the first 5 people have no rare variants. Person 6 has 1 rare variant. And for the most part, you see everybody's a 0, but there are some 1s. There's a few 2s, and there's even some 3s and a couple of 4s, which is, so this person over here has 4 rare variants within the region. Right, but that's all it is. It's simply a count of the number of rare variants for each individual within the region. Line 43 is actually going to then associate this count, this dosage, with the phenotype of interest. Highlight it and then hit run. In this case, you see that the p-value for C, so again, this is the coefficient matrix, what we're most concerned with, at least for this example. The p-value in this case is 0.026, which is slightly more significant than what we had by using the cast approach. That's not always going to be the case, but at least in this case, that's what happened. So this was just doing count-based collapsing. The next step is we're going to actually see what happens if we include some weighting. So the first set of weights that we're going to calculate are the Madsen and Browning weights. So the weights that arose from the weighted sum test, except we're using all individuals instead of just the controls. So here the weight is going to be 1 divided by the square root of the minor allele frequency of the rare variance times 1 minus the minor allele frequency of the rare variance. Then line 49 is simply creating the weighted sum, in this case, based on the Madsen-Browning weights. And line 50 is, again, running the actual regression to do the hypothesis test. So we're going to run lines 48 and 49. And then if you look at the variable C now, It's again just a whole bunch of numbers, but they are no longer counts. So whereas before all of our data were constrained between 0 and 1 for the cast approach, or 0, 1, 2, 3, 4 for the count-based collapsing, you now see that the range of the data of these values is much higher. You have a whole bunch of zeros, but you have some that are in their 40s and perhaps even higher. So we're now upweighting for the effect of rarer variance. Then to actually do the association test, we're going to again just run a simple linear regression. That's line 50. If we hit run, what we see over here is we get a p-value of 0.0136, which is even slightly more significant than before. Next, we're going to consider an alternative weighting. So now we set the weights to be equal to 1 divided by the square root of the minor allele frequency of the rare variance. And then we again generate a collapse value C and again run the association test. So we're going to run all three of these lines at the same time, line 52 through 54. You hit run, and you see again the p-value is 0.0136, which is basically the same thing as what we had before when the weights were slightly different. Here, note that it's 1 divided by the square root of the minor allele frequency. We also have 1 minus the minor allele frequency. And the reason why these end up as being very, very similar is that for very rare variance, 1 minus the minor allele frequency is pretty close to 1. And so it really doesn't figure into the weights very much. It really doesn't affect it very much. So for the most part, we're going to ignore this component going forward. But here, what we're going to do, line 56, is consider an alternative set of weights where instead of dividing by the square root of the minor allele frequency, we just divide by the minor allele frequency itself. So this is a more aggressive weight. So let's see what happens if we do this. So that's line 56 through 58. Hit run. And you see, oh, in this case, your p-value is 0.0583, which is, strictly speaking, not statistically significant. There's some people who would just truncate the 83, but that's not very good statistical practice. What did we see? If we do 1 divided by the square root of the minor allele frequency, we're able to get something that is relatively significant. On the other hand, if we do use a more aggressive weight, which is to say we give the rarer variance even more influence, we drop out of the range of significance. So with that in mind, let's try another set of weights. So here, instead of 1 divided by the minor allele frequency, we're going to square that. So that's to say it's an even more aggressive set of weights than before. So rare variants are given even more weight in this case. So if we run line 60 through 62, wow, in this case your p-value is 0.24, which is nowhere near anything that would be called statistically significant by any modern standards. So what this suggests is that if we give the very rare variance a lot of weight, a lot of influence, then we're no longer able to call significance. On the other hand, if we do a little bit of weighting, then we are able to get some significance. So let's see what happens if we use even a slightly more modest set of weights. So here it's 1 divided by the minor allele frequency, but instead of taking the square or square root, I should say, we're going to take the cube root. So this is even less aggressive than the square root weights. So if we highlight this and then hit run, you see we get a p-value of 0.012, which is slightly more significant than if we had used the square root. This illustrates a number of different points. First and foremost, it shows that the choice of weighting does in fact matter. If you use a very, very set of aggressive weights for this data set, you're not able to call significance, suggesting that it's not the very rare variants that are driving the association. However, it is the rarer variants that have an effect, but it's simply not the very, very rare ones that are driving it. So if you upweight, then you do gain a little bit of significance, but if you give too much weight to the very rare ones, you drop out. So that suggests that it's probably some of the variants that have middling allele frequencies that are actually driving the association. In practice, one should not search across lots of ranges of weights. These should be pre-specified a priori and to avoid data fishing. However, one can do post hoc analysis to try and tease apart what is going on. But these p-values should then be taken as inherently biased and not treated as normal p-values because you've already done a hypothesis test to get here. So again, just be careful. Don't run too many sets of weights and do data fishing in order to call significance. All right, so moving on, what we've done so far is we've looked at trait 1 and gene 1. The next set of things we're going to run is repeat what we did, except we're going to look at gene 2 and trait 2. So again, what we're going to do is we're going to read in the data. So z equals as.matrix, read.table of gene 2. We run this, and just to see what this is, z is again just a giant matrix of zeros, ones, and twos. If we look at the dimensionality of z, there are 1,000 individuals and 62 variants within this particular region of interest. The next step is we're going to calculate the minor allele frequencies, and then we're going to read in the trait values, so the outcome. Highlights lines 74 through 75, hit run. All right. Then again, it should say you read in 1,000 items, so one trait value for each individual. Where then next, for line 78, gives us the indices of the variants that have allele frequency less than 3%. We hit run. Okay. And then next, we're actually ready to do the actual testing. So lines 83 and 85 generate the collapsed variable and do the hypothesis test respectively. We highlight those, hit run, and you see that the p-value for the association between the collapsed variable and the outcome is 0.15. Not much going on over here. Let's repeat this doing count-based collapsing. So that's lines 90 through 91. We hit run, and again you see that the p-value is 0.32. Again, not very much interesting going on. Let's again just try a weighted count-based collapsing. All right, lines 96 through 98, and we hit run. And again, not much going on. The p-value is 0.4, nowhere near anything that would be called interesting. Using these collapsing-based tests, we don't see gene 2 as being related to trait 2. Now let's move on to gene 3 and trait 3. All right, and we're going to do to run a number of analyses using some of these different tests. So the first thing is we're going to read in the data. So that's line 105. Let's look at what z is. Again, it's just a giant matrix. The dimensionality of z is 1,000 by 57 columns. So that's 1,000 rows, 1,000 individuals, 57 variants within this particular region of interest. Lines 106 through and 107, calculating the minor allele frequencies, reading in the outcome trait values. And so if we hit run, you see we have the MAF and we've read in 1,000 traits. So now what we're going to do is we're going to run binary collapsing, looking across a range of different thresholds. So the first step is, again, we're going to figure out which variants have allele frequency less than 5%, and then we're going to test for the association between the collapsed variable, where it's the number, whether you have any variants less than 5%, and our trait of interest. So lines 1012 through 114, we hit run, and you see p-value 0.55. So you think probably not very much going on. If you've treated the variants with allele frequency less than 5% as rare, we really don't see anything interesting going on. All right, just for fun, let's see what happens if we set the threshold to be 3%. All right, we highlight lines 117 through 119, hit run. And again, not very much going on. The p-value for the association between the rare variants and the outcome, 0.29. Okay, so again, you would conclude probably not very much interesting going on over here. Now let's try to see what happens if we set the threshold to be 1%. We hit run. Oh, wow. So now, if you look at your p-value, it's now 0.0052. So just by changing the threshold from 3% to 1%, you go from having a p-value of 0.29, which is, say, not very much, nothing interesting there, to a p-value of 0.00524, which at least at the nominal level would be called statistically significant. All right, so let's set a threshold that's even more stringent and say let's call the variants that have allele frequency less than 0.5% as rare, and see what happens if we do run the analysis now. So we repeat this, and wow, now our p-value is on the order of 10 to the minus 5. So e minus 0.05 means times 10 to the minus 5. So our p-value is 8.25 times 10 to the minus 5, which would be called very, very significant, at least if we're using the nominal significance level. So this illustrates a number of different points. First of all, it shows very clearly that the choice of threshold can be very, very important. So by choosing the right variants to test, you can actually gain a lot of power. The problem, of course, is that it's very difficult to tell a priori which set of variants should be tested. That's why the variable threshold test of Alke's Price's group, which searches across a range of different thresholds, a range of different grouping structures, is actually very, very nice and very, very powerful. Right? So the variable threshold test addresses this particular problem and develops an omnibus test within this context. And it is an approach which is commonly used. Okay. This other thing that this illustrates is that at least for this particular gene, it's likely the variants that have very, very low frequency that are driving significance. The relatively common variants that are rare, but not that rare, are probably only contributing noise. But the very rare variants are more likely to be the ones that are causal in this case. So we can repeat the same thing using count-based collapsing. So we'll run through that very quickly. Again, allele frequency less than 5%, nothing called significant. Allele frequency less than 3%. If we run this, again, nothing called significant. Now we set the threshold to be 1%. We hit run again. Again, now you see a p-value of 0.053. This is not as significant as what we saw using the binary collapsing, but it's still a lot better than what we saw setting a threshold of 3% using count-based collapsing. If we set the threshold to be 0.5%, hit run, you again end up with something that's pretty significant. In this case, note that the p-value from using the CAST approach is actually smaller than the p-value by using dosage-based collapsing. All right, now let's, again, focusing in on gene 3 and trait 3, look at weighted count-based collapsing. We're again going to look at the variants that have allele frequency less than 5%. All right, and we're going to do a weighted count-based collapsing where the weights are 1 divided by the minor allele frequency. So if we highlight lines 153 through 156, we hit run. You see a p-value of 0.00021, all right, which is pretty significant in this, at least at the nominal level. However, note that when we did count-based collapsing or CAST, nothing was called significant at this threshold. And so what's going on here is the weights are effectively downweighting the common variants, and you're giving a lot of weight to the very rare variants. So that basically overcomes the thresholding issue. So by giving, in this case, a fairly aggressive set of weights to the variants, all right, the common variants and the relatively common are not really contributing very much to this weighted sum, and so their influence is diminished, and you're still able to call significance. In fact, we're going to repeat the analysis in lines 158 through 160, where we set the weights to be 1 divided by the minor allele frequency, but we're no longer restricting the analysis to only the rare variants. And so if we run lines 158 through 160, highlight those and hit run, you see again the p-value is basically very similar to as if you had first restricted attention to the variants with allele frequency less than 5%. P-value in this case is 0.00027, and here it's 0.0021. So you lose a little bit of significance, but it's very, very close. And the reason again is that even though you're including common variants in here, because they're given such small weight, using weights that is 1 divided by the minor allele frequency, then they don't contribute very much to the overall weighted sum from a relative standpoint. So again, this illustrates a number of different points. The first one is, again, that the choice of threshold matters, and that weighting sometimes can diminish the impact of the particular threshold, assuming that you want the more rare variants to have higher influence. So that concludes most of what I wanted to illustrate with regard to the collapsing-based tests.